Thank you. Gracias. So this is roughly the plan. So I'm going to be talking about distributed transactions, starting with the basics, and then eventually go into what we do in Orleans with transactions and why and how. So let's start with the basics. Like a canonical example of a transaction is we need to transfer, say, $100 from account A to account B. What do we want? Right? We want all or nothing, which is atomicity. We don't want deposit and not withdraw money or the other way around. We want to maintain consistency, so some logical constraints, for example, no zero, below zero balance. We want to have isolation, so while we add in money to account B, we don't want it to be visible to another transaction in case that transaction fails and this money will end up not in the account. And we want everything to be durable, so we want a persistent state, data stored somewhere in reliable store. So in general, like this property has been available since like early 70s, I believe, and database management systems like Oracle, so SQL servers of the world, they've been taking care of all of that. The problem is it was all on a single machine. So data is local, there's no network involved, anything that fails, fails on the machine, so it's all great. It's much simpler of a problem to solve, and the most focus in database was on this trade-off between isolation, consistency levels, and performance. So if you lower some of those guarantees, you can have a higher throughput. And that's why there is this range of consistency model support and the range of isolation modes. But if we go to distributed transactions, it's a very different game. So in distributed transactions, you have different databases or systems, they're called resource managers, and you have the coordinator. Like in the Microsoft world, it's called Microsoft Distributed Transaction Coordinator, MSDTC. There are other implementations, and there is a protocol, XOpen protocol for that. So how it works, our application code first calls transaction coordinator to get unique transaction ID. And then it starts doing operations with these resources by passing this transaction ID until it's done with everything it needs to do as part of a transaction. And then it starts the process of committing transaction by doing so-called two-phase commit. So we need to call the coordinator, and then coordinator calls the resource manager, say prepare for a commit, and then once prepare is succeeded, transaction can be committed. So it's a well-understood protocol. It was developed in the 70s, implemented in so many different places. There are problems with that. So even though it's all nice and cool, the reality is there's the complexity of configuring these kind of distributed systems. So I took a snapshot from one of the blog posts about how to configure. It's a Microsoft blog post, how to configure Microsoft Distributed Transaction Coordinator on Microsoft platform, on Windows, how to configure firewalls and ensure communication between application server and DTC. So it's not trivial if these kind of blog posts are needed. Compatibility is in theory there, but in practice, if we try to coordinate multiple different systems, you run into different implementations of the same protocol. But bigger than anything is the problem with performance. Because of these round trips with transaction coordinator, and because of locks that you need to take and all of these factors, throughput generally is low. So the systems were built decades ago for transactions rate of tens per second, maybe hundreds. So if we move to modern systems, that's usually not enough. And the root of this problem is really the cap theorem. So who's familiar with the cap theorem? I hope everyone, right? So it states that it is impossible to achieve both consistency and availability of distributed systems when your network isn't perfect, when you can have network partitions in your system. So you have to choose between either consistency or availability. Either you have guarantees of the consistency of your data, or you have to trade it off and say my system is unavailable when there are network issues. So the switch to new kinds of applications, the web scale, the internet age, the conclusion essentially was that distributed transactions are not going to work. They're not going to cut it. That's why they're called dead. And to me, the manifestor of this idea was this paper published, I believe, in 2007 by Pat Helland. And it's interesting because Pat was one of the early people in transactions. So he worked with Jim Gray, he worked on tandem systems. So he's the transactions guy, he's the database guy. And so he stated, and I try to underline this key statement, that for new kinds of application, developers need to think how to build application without distributed transactions. Sort of forget about them. They're not going to work. So that's the claim that distributed transactions are dead. I highlighted in green his other statement where he speculates that in the future there may be new approaches, new kind of middleware solutions emerge that would address this problem, but he doesn't point to those solutions. And some workarounds and some approaches, of course, emerged and became popular. Like one of them is CQRS, command query responsibility segregation. I think Greg Young coined this term. So the idea here is to separate the read and write path. So all the reads, they go into database at the bottom, the event store. So you append all the changes to event store, and then asynchronously you move them to the upper store where you serve reads. So writes go one path and reads are served from the other in the data store that is organized differently. So the key here is the events are getting updated, appended to the event store. And I took it from this publication, it's freely available from the Microsoft Patterns and Practices group. What's interesting is one of those people, Julian Dominguez, he worked on Orleans on my project for a couple of years. So to illustrate how it works, so with event sourcing, when our application receives a request to transfer $100, the first thing it does, so the request arrives to some entity, some object, some whatever system, service that represents the bank. And the first thing we do, we take this request and we write it to our event store. So that information contains the request and it has a unique ID so that we can track and manage it. So once that is done, we can respond success because the request was recorded. Later, asynchronously, we execute this request. We call the account entities, like account A, account B, and send different commands. So withdraw from one, deposit to the other one, and they do the same. They take this event that they received and they add it to their event queue. So as you can see, this works generally. This can scale because we write events, we don't take locks. But the problem is, out of all these ACID guarantees, atomicity, consistency, isolation, we really guarantee only durability because there is no guarantee that these operations on account A and B will happen at the same time. There is no guarantee that some other transaction will not see partial results. So we kind of end up with only D. And that's fine for a lot of applications, but what if we need more? This is a very popular pattern, don't get me wrong. This is a very powerful pattern that's used in many applications, even in financial applications. And if you talk to people building financial systems, they will tell you that actually a lot of financial transactions are eventually consistent. So while this was happening, I claim the strong consistency people decided to strike back. And if you've seen that in 2012, this Spanner paper was published at OSDI, and in the motivation part of it that I enlarged, essentially they're saying that Google engineers, and Google hires generally engineers above average, so they're very smart people. But in this motivation piece of the paper, they're saying these engineers have difficulties dealing with eventual consistency. They cannot handle these complex cases, so they're making the argument for a strongly consistent system, and that's why they build Spanner. And in Spanner, when they explain Cloud Spanner, they show this table where there are properties of single machine systems, strongly consistent, and the properties of NoSQL stores. They claim that Cloud Spanner combines the two. So you have this green checkboxes on one side and green checkboxes in the other column. They get merged into Spanner. So it seems like a magical system that is solving all the problems in the world. So it claims to be a so-called CA system that gives you both consistency and availability. But the author of the CAP theorem, Eric Brewer, he works, I think, 80% for Google and 40% for Berkeley. He is a scientist, so he cannot claim something that's physically impossible. So he published a paper explaining, and I highlighted where he's saying that Spanner is effectively CA. So in reality, when there are network partitions, it's a CP system, so they optimize for consistency. If there are any network issues, the system will be unavailable until network issues are resolved. But because Google can control the whole network, all of their fibers, all of their switches, software and all their switches, they're saying our network is so reliable that we can reduce the probability of network partition and we get effectively CA system. So the alternative solution is Cosmos DB that was kind of built in parallel at Microsoft. And it's a globally distributed JSON document-based database. And it has different properties. It shows, it gives like the choice of 5 consistency models, from strongly consistent to eventual consistent, 3 in between. And actually talking to those people, the extreme ends of the spectrum thrown in the eventual are least popular. The middle ones are the more popular among the developers. So this system makes a different choice, saying you choose your consistent guarantees, and as a result, you get performance in other properties. But if we step back, if we look at all the systems, I should have mentioned the CockroachDB because Rebecca is here. But I think if we step back, still, with all these approaches, you get a single database. So you have to buy into this database, and if that works for you, that's fine, that's great. So you build the application, the database that gives you all these properties. But that limits you. The moment you need to combine two stores or have some kind of more complex solution, or maybe you don't want to be locked into a solution, you don't really get anything. So either you get SQL or Cosmos DB or Spanner or not. So Orleans is the project I've been working on. I presented 2 years ago here. I'm not going to go into a lot of details, but just cover the basics, and you'll see how we arrive to the topic of transactions. So Orleans is the framework for the cloud. Technically not for the cloud, it's for building distributed systems. So its goal is to provide developers a very simple programming model that they can write very much less code than otherwise, at the same time allow them to write applications that scale by default, so that when you need to scale 10 times, 100 times, 1,000 times, you will need to tweak your application, but you would not have to throw it away and rewrite. And in Orleans, the programming model looks like this. So in this middle tier section, instead of stateless servers, you have the cluster of machines where these distributed objects live. We call them grains. Technically, they're virtual actors, but it's easy to think of them as grains is just the distributed object with a stable ID. So you have an object for a user with, say, phone number or social security number or email. So by this identity of the user, you can always get a reference to the object that represents the user and then make a method call to it. So it kind of manages your resources of your application by bringing to memory objects that you recently use or just need now, and then phasing them out if they're not needed anymore in memory. So these objects, these grains are isolated. They manage their own state. There is no direct access to other grains' state. You have to send a message by making a method call. And that makes it great for scalability. Because you don't need to coordinate really between the state, and you can put these objects on different machines. They send in messages to each other by making method calls anyway. So whether they're on the same machine or on different machines, it doesn't make any difference for the application. Slightly higher latency, but it's not really that much. Because grain manages its own state, it isolates it from all other objects, all other grains in the system, and it's very compatible, for example, with event sourcing. So you can just append events for this object and store it and manage it. And different classes of grains, they can store their state in different databases. It's not tied in any way to a single data store. So you can distribute it across different technologies that are suitable for different kinds of grains. For example, the user profile versus session that is in real time and things like that. But the downside, again, it scales well, but the downside, there is no built-in coordination. You cannot achieve any kind of guarantee. So if you look at ACID, it's kind of, again, the same picture. There is D there, there is durability, but there is no atomicity, consistency, or isolation guarantees. And people that have been building Orleans application, they wanted that because they need to build, like in gaming where a lot of Orleans usage, they need to do virtual commerce. They want to exchange atomically gold coins for cannonballs in the game. And they don't want to be like out of balance where things are not consistent. So in Orleans, in general, this operation, the canonical operation of transferring $100 from account A to account B looks like this. So the front end, like the web server, will receive a request to transfer, and it calls the bank grain, say, hey, I need to transfer from A to B. Bank grain calls two other grains, grain A and grain B of those accounts, and gives them deposit and withdrawal request. Grains independently update their state in the database, and then respond, okay, everything is fine. Operation completed successfully. So it all looks great when everything succeeds. But of course, we'll understand that this write to database may fail. Or maybe the write succeeded, but the message was lost during the network operation. Or maybe the message between grains got lost because, again, the network isn't perfect, and machines get rebooted and things like that. So with all of this, you don't really have a good solution. So what what people end up doing, and I've seen the implementation of that in several applications. So in order to make this work, this is what you need to do, roughly. One of the options, not the only option, but one of the popular patterns. So bank grain receives a request. The first thing it needs to do is to record this request. And record with a unique ID, so when the operation is retried later, it can dedupe it and say, oh, I already received it, it's already in my queue for execution. I will not transfer the same money, for the same request twice. So it records it, and then needs some kind of recovery mechanism. In case everything goes wrong, machines get rebooted, I need to be able to re-execute this transaction that hasn't completed. Like in Orleans, we have this built-in mechanism of reminders there, kind of persistent timers. You can say, oh, remind me after 5 minutes or after an hour, and I can recover. So only after that, only after set up this recovery mechanism, I can call these grains, and they need to do something similar, and then they do all the work and return back. And once operation completes on the right-hand side, then we need to record in the bank grain state that we completed the operation. So again, if everything shut down and restarted, we know that that operation completed. Then we remove the recovery mechanism, and then we return success. So this is even the simplified version of what people have to do in reality to provide any kind of guarantees. And I put this copy of, I think Martin is here somewhere, and I put it here not because he would be here. I only gave a talk with this slide. So this observation by Martin that in any complex system, almost, like you can find some half-implemented semi-transactional mechanisms. So what I just showed you, I think, is a good illustration of that point by Martin. So what we really want, I would argue, is what we used to have with normal distributed transactions. So we need to have transactional operation that is marked as it requires a new transaction, transfer requires a new transaction, and then operation on deposit and withdrawal, they mark as the required transaction, and everything else to be done by the system. That's what we really want as developers. We don't want to write this complex code of deduping and recovery and all of that. Right, so everything completes. So we really want asset guarantees, which is a very obvious answer, right? So if we started, for example, with $500 in each of the accounts, so we want to atomically move to 400 and 600 state, and if something goes wrong, if something failed, we roll back abort to the state as before, as if nothing happened. So I would argue that that's what we want as developers. And that's exactly what release transactions provide in this case. So if you look at some code example, this is what the method for transfer on the bank grain, this iBank grain interface of that grain looks like. So transfer has this attribute saying transaction, very familiar from, I don't know, MTS, COM+, JTE notation. Say this operation requires a new transaction. And takes 3 arguments. And then likewise on the account grain, we have operations marked with required transaction. Not just withdrawal and deposit, but also get balance. Because remember, to guarantee that we see only a state that is consistent and with transactional history, we have to be transactional even when we just read the state, like get the balance. So that's what you do in the code. And so the transfer operation becomes really trivial because of this attribution and all sort of the magic done by the runtime. We essentially get references to 2 grains. Then we call methods on both of them. They return a task. So who knows what a task is in TPL and .NET? Because I know not everybody is from .NET. So it's essentially a promise. So it's a promise, or it's not quite a future. It's a asynchronous future. So you get these 2 tasks, then we join them and return the joint task. It will be resolved when both operations complete successfully, or it will be failed, broken if there is any failure in the process. That's it. That's all the code we need to write here. So on the count grain implementation side, we're using dependency injection. So at the bottom, you see the constructor. Through dependency injection, inject this balance of type iTransactional state of balance, and balance is defined above as just a single integer property. And that's what we use in the grain code. So deposit is simply decrement or increment and withdrawal decrement operation. And get balance is single line. So that's really what you write, what kind of code you write. Yeah, that's really what you need, except for some configuration. It's a pluggable system. You can plug in different implementations of transaction log, different cluster. So we have this notion of servers over Orleans. They're called silos. So you need to configure the server when you start it. But after that, your application just works. So of course, that's not interesting without kind of understanding what it looks like. How is it implemented? What does it do under the covers? And this paper that was published a couple of years ago by Phil Bernstein and Tamer Edlib, it described the system. But in terms of architecture of the system, this is the architectural diagram. I'm not joking. That's the only architectural diagram in the paper. So I decided to kind of zoom in a little bit and show more details. So in reality, so this is the cluster of silos of the servers over Orleans that run. The one thing that gets added in the system is the notion of transaction manager. And it was designed to be a separate server. So you run a separate server that coordinates transactions. And inside each silo, you have a transaction agent that is responsible for relaying operations on behalf of all the grains. And you can have hundreds of thousands of million grains in each silo. So instead of all of them talking independently to transaction manager, you have transaction agent that combines that or multiplexes this communication. And notice that storage is completely decoupled. So different, like I said, different grain classes can use different storage. You can use SQL, you can use blob, you can use even file system. And there is a separate storage requirement for transaction manager, for transaction log. So that's what they all color differently. For reliability, you might want to have a standby transaction manager because it's a single bottleneck in the system or a single point of failure. So in case it fails, you want to have another one that will quickly start read a transaction log and continue operation. So it's really the implementation of classical two-phase commit. So this is how transactions happen in the system. So request arrives to the bank grain, and the silo where bank grain leaves, that the silo hosts this grain, it becomes transactional coordinator for this transaction. It makes a call to the first grain, grain A, with withdrawal request. And when grain A performs this operation, it puts a lock. So now grain A is locked until this operation completes. So another operation has to wait for execution. So it returns back successfully, perform the withdrawal part, and as part of the request response, it returns a list of dependencies. So if we execute in transaction N, the A may return that this transaction depends on uncommitted transaction N minus 5. That's all done automatically within the system. The application doesn't see that. Likewise, the deposit call to the grain B, which can be in a different silo, puts a lock on grain B, and the response returns list of dependencies. So in this case, it's N minus 2. That's what grain B depends on. So once it's all done, once the operation is complete, we can move to prepare and commit, the commit process of the protocol. And that happens automatically. Before returning response to the caller, the system will do prepare calls to all the participating transactions, participating grains in this transaction. And as part of prepare, they persist state to their persistent store. So they're ready to commit this operation. So once prepare is done, locks are removed. So actually lock is held for a very short period of time. So it's so-called early lock release. It's an optimization to improve throughput and reduce latency. So we remove locks, and now we prepare. The data is ready. It's already durably persisted in the store. So we're ready to flip the flag and say this transaction committed. And before we can do that, we have to call transaction manager. This is where this one big entity, a single point of failure gets in a way. So we call it and say, please validate transaction N. And transaction N includes grains A and B. And this transaction depends on transaction N minus 5 and N minus 2. So that's a request. The only job that transaction manager does is validation of transactions to make sure there are not conflicts and no violation of constraints happen. So transaction manager sees the dependencies. It has to wait for these dependent transactions to complete. So once they complete successfully, it knows that now I can approve this transaction. So it writes to transaction log and saying transaction N committed. So after that, there is no way back. So transaction committed, it's already recorded, and there is a recovery phase, even if you shut down the system at this point, just like with traditional two-phase commit. And after that, it responds, say, committed, and we can say, okay, success. So if something fails, if any of these if validation transaction fails in transaction manager, for example, a dependent transaction n-2 aborted, it just responds to abort. The transaction failed, and then there is error, so you have to return an error. So it works, but and this is kind of the original version that was implemented, and we put it in our code base. But there are obvious drawbacks. So one of the drawbacks is you can have cascading aborts. Because of these dependency chains, you can get into a situation where one failure can trigger abort of all dependent transactions. But in this paper, Phil and Timer, they prove that it's only possible when there is a real failure. When there is server failure, operating system failure, it's not part of a normal protocol execution. I kind of, I didn't talk about this, but I mentioned that get balance operation requires, it has to be transactional so that we don't see uncommitted data. And because of that, even the simple read operation requires a round trip to transaction manager and it has to wait for a lock and for latency of this operation. So this is just inefficiency in the system. So correctness-wise, it's all good, but it's inefficient. And of course, standalone server, you have to deploy it, you have to configure it, you have to monitor it, you have to have standby and all of these operations that are just extra operational cost configuration. And everyone asks about, so what about throughput? So you have this single point of the bottleneck in the system. Yes, that's true, but the argument here is not to use transactions for everything in a system. So if you only use it for financial operations, for example, when people bring money through your application, then the throughput can be high enough for most of those applications. That was the argument of the original design. And we can improve throughput even with this design. Like for example, the old trick that instead of validating single operation, single transaction, we can validate a batch of transactions. So instead of doing 5, 10, 100 round trips, we can send one message to the transaction manager and then get a single response that includes the list of transactions that committed and transactions got aborted. So we can batch and then improve throughput. In the paper, these numbers that were tested with the original design, they show that you can roughly run 150,000 transactions per second, 150,000 transactions per second with a single 8-core transaction manager server. So if your business runs the application that generates 150 financial operations per second, I would argue you have a good problem here. So you have a very good business. So that's why I like this argument that a single thing doesn't scale, doesn't run. It has to be applied carefully because it may be more than enough. So we see like a lot of systems that they do the hundreds of operations per second, and maybe a few thousand. So they have a lot of headroom here, even with the single bottleneck. But this design that I described was the original, like a couple of years ago, was a prototype, and we integrate. So we ship it as beta. We had a big release of Orleans in March, Orleans 2.0, that was focused on making it cross-platform by being compatible with .NET Core, so you can run Linux on Mac OS. So we included transactional functionality in beta form, which has the single server operation. But we continue partnering with Microsoft Research. So this is where Orleans project started in research back many years ago now. And since then, we moved to product group with my team, but we continue working with research and collaboration. This is one of the collaborations on transactions. And we had last summer, this couple interns, Christopher Mickeljohn, he talked here last year, I believe, and Alejandro, they both coming to Redmond as interns this summer. I think Chris is already there. And Sebastian and Phil, they sort of lead the work there. So they worked last summer on the new version of the protocol. So we call it Transaction Manager V2, where it's a simple kind of trick. I mean, everything is simple in hindsight. So instead of talking to this individual, this standalone transaction manager, why don't we make the grain itself transaction manager? So when the request arrives to our bank grain, since that's where transactions start, that grain becomes the transaction manager for this transaction. And yeah, it needs to have its own transaction log, but now it scales. Now every grain can start a transaction, so you don't have a real the bottleneck in the system. So it's a very simple improvement. I mean, simple conceptually. There's a lot of code that's involved in this, of course. But if we look at the original list of drawbacks, we see that the single grain transactions, they can now be executed and validated on the grain itself. So it doesn't need to talk to any other entity. So there is no round trip that is needed for read operations. So we address that. Like, there is no standalone transaction manager, and there is no centralized transaction manager in the system. So it scales. Cascading aborts is still a possibility, but out of the 4 drawbacks, I think we addressed 3. The best of it all is that it's all open source. I mean, it's not some proprietary system that I tell you, here's how it works, you need to trust me. And no, it's all there. It's all on GitHub. The whole development is happening on GitHub. And I put this picture. So this is the repo. This is literally the pull request with V2 version of Transaction Manager, of Distributed Transaction Manager. And then there's an example. This is somebody from the community, not from my group, not from Microsoft. This guy, Jay Stainage, I forgot the full name. So he implemented transaction log provider for, I believe, DynamoDB for AWS. So it's completely open. It's not tied to any kind of technology. It can work on any storage. So if you wanted to work on AngularDB, just write a provider and you can work. And in general, this is one of those projects that is completely open. People talk about new Microsoft, but we kind of started before that notion was really kind of mentioned. And it's a lot of fun just being in the open and working with all these people that all around the world. So project is there, they use it in their applications, and they come and contribute. The contribution can be like a bug report or a bug fix or a feature or a provider. So it's all happening completely in the open. So what I wanted to conclude this talk with is kind of a few claims. One is, sort of to my surprise, in the beginning, there's still a lot of space for innovation. So you kind of, at least I don't know about you, but I thought about the transactions is kind of solved problem. Like, why would we care about it? It's already, like, these people in the 70s and 80s solved all the problems. But in reality, there is a lot of space for innovation. And for example, the CockroachDB, I think, shows that, yeah, a lot can be done in database. And this whole transition from SQL to NoSQL to kind of almost SQL, Mike Stonebreaker calls NoSQL is not yet SQL. There's still a lot of unknowns there. There's still a lot of things to do. So it shouldn't intimidate us that, oh, transactions were invented in the 70s, for example. The other claim, maybe even stronger, is that we forgot, I say, that how much can be done in the middle tier. So if you look at traditional applications, including most applications today, they have stateless front ends, stateless middle tier, and database. Really, it's like 3-tier, or if it's n-tier with cache and whatnot. Still, the middle tier is very simple. And that's what we try to change with Orleans, where you have stateful middle tier that can have state in memory, can manage a lot of stuff. And that allows to do many other interesting things that you wouldn't be able to do when you just integrate it with some database. So this kind of claim goes way beyond Orleans, that in middle tier we can do a lot of interesting functionality that we almost like forgot how to do, because we all switched to this kind of NoSQL, high-scale, stateless architecture. So that's my claim, that we should do that, and that allows us to be agnostic of storage. Kind of like in my examples, all these grains, they can use different storage. We can do transactions across of the systems that were not designed to be transactional. We can use, because of the power of middle tier, we can have ACID transaction across non-transactional storage. Why not? And I keep saying open source because that should be the default. My claim is that today, instead of getting permission to open source something, we should reverse our thinking. So when something is done, we should get permission not to open source something, because most software, like, you cannot sell. Like, you cannot sell a framework. So software should be by default open source. I mean, at least the back end. And I think that's what we're doing, and that's, I welcome everybody to participate and look at the code and contribute and try it. And that's all I had. So, muchas gracias. Thank you very much.